Okay. So, coming back to waves in space time and propagation, what we had figured out is space time does not remain the same if there is a direction that is involved to distinguish one from the other. And in the process, we have realized that there is some kind of a transformation that is called the Lorentz transformation. The associated symmetry is Lorentz symmetry. The algebra is of the generators is the Lorentz algebra, and there was one transformation that we have been aware of, that was the rotational transformation about an axis, and for 3 independent axes there were 3 such possible rotations, and the realization of one of them about the third axis was what was given by equation number 23, and the others could be figured out in a similar fashion. All right. Anything else? Well, looks like there is that we can in principle invert this matrix. So, if we can invert this matrix, this is a non-singular matrix, and if it happens to be a non-singular matrix, then for a rotation in the clockwise direction about an axis, let us say it is z, there exists a inverse rotation in the anticlockwise direction about z, and when you combine them with each other, you basically get no rotation. That is the identity. So, this is one aspect of the Lorentz symmetry, and was our motivation at the beginning to inspect the nature of certain observables, variables, and see whether they retain their forms under rotations or they degenerate into something else, which is different from where we had started with or what we have anticipated. Okay. So, till we come to that particular point, we have left out another symmetry operation which is called boost. So, let us see what are the consequences that we face when we take boost into account. It is not very difficult, but little lengthy and tedious. But if it is executed properly, then one again finds out the result of finite boost transformation in the third direction, and the result is a matrix in terms of a parameter that we have defined by the quantity chi. This particular quantity chi that we have here and the elements of this matrix written as cosh chi or sin chi does not really resonate with what we had learned in our lessons of relativity earlier, till we realize that there is a transformation that can be given by chi equals tan hyperbolic inverse V by C, when V is the velocity of one frame with respect to the other, then this e to the power chi n3 actually gives, there is a typo in equation 28, it should be replaced by n3 equal to this matrix gamma and gamma here. These are the Lorentz boosts given by 1 over square root of 1 minus v square by c square, and these are the off diagonal pieces, and it actually corresponds to the Lorentz transformation about some axis that we have come across in our other courses of physics. So, to conclude here, we would like to say that a Lorentz transformation basically are divided into two groups. One of them correspond to rotations and the other is boost. These are the two things that compose a Lorentz transformation. So, boost, like in the case of rotation, also preserves the norm of the inner products, but the direct products are always a casualty. They are not preserved. So, as a consequence, if our observable quantities happen to be made up of inner products in a vector space, then there is no problem about them. But if they are made up of outer products of the elements of a vector space, then they may not remain invariant, another transformation of coordinates or another coordinate transformation. So, you have to look for other alternative ways to make sense of this extra interference that is coming from change of the coordinate system. And that is something that will come back when the time is appropriate. Thank you.